say that chemistry's my hustle, and your brain is like a muscle. So settle in because it's time to flex. Okay, here we are again, day 5. We're still talking about this contamination that caused the fish kill. And in day 5's lesson, we're actually doing a little review of what we talked about last week, which is nice. We get a day to actually practice what we had learned. And there's a simulation, a very good simulation here. Let me pull it up. And in the simulation, we're actually able to adjust. There's a couple of inputs. Let me show you a couple of inputs here. First, we're able to change the different chemicals. Let's just throw a random chemical in there first, cobalt chloride. And I'm able to add different amounts of cobalt chloride. That is our solute. I'm also able to add water, which is our solvent. And finally, we're able to track the concentration. So 2 inputs and 1 output. Again, the inputs are the amount of solute. Notice how that changes our concentration. The amount of solvent. Notice how our concentration changes when I add solvent. And our output is the concentration in units of moles per liter. So then that show up under the practice for molarity. We're either asked to find the number of moles of solute, the liters of solvent, which is almost always water because it's the universal solvent, or the concentration. If you're asked to find that output value, the concentration, it's going to be in molarity, and the equation is nice and simple. Molarity equals moles of solute divided by liters of solvent. So we can just plug those values in to get our concentration in units of molarity. But what if we're asked to find one of the inputs? What if we're asked to find either the moles of solute or the volume of solution? Let me give you an example. In number 3 here, we're given milliliters, molarity, and we're asked to find the number of moles of HCl. It's as if I asked a problem, if I want this strength and I want this volume, how many moles of HCl am I going to have to dissolve? Anytime you're given a problem like this where you're asked to find either the moles or the liters, the 2 inputs, use the concentration as a conversion factor. 2.0 molarity is the same thing as saying 2.0 moles of this solute are dissolved per liter of solution. Yeah, we don't have 1 liter of solution, but we know that if we did have a liter of solution, 2.0 moles would be the amount of moles that's dissolved in that liter. This is our conversion factor, so we're not going to start with this. Let's start with our milliliters. You've probably noticed that with molarity anyway, it's always per units of liters. So we have to convert this from milliliters to liters. And that conversion is 1 to 1,000. And now we can use the conversion factor that was given to us in the problem. We know that we can convert from liters to moles because for every 2.0 moles of solute, there's 1 liter. That's what this conversion factor is saying. So now canceling out my units, let's just double check. Milliliters cancel, liters cancel. I'm left with units of moles. And from there you can calculate out the number of moles of HCl that would need to be dissolved in 40 milliliters of solution in order to get a 2.0 molar strength solution. Okay, last thing to review here is just this idea of determining products. The nice part about with the solubility rules here is you know that it's going to be a double replacement reaction. You know, where we have AB plus XY. It's like we go to the prom and there's 2 people that are dancing, 2 couples, and they decide to switch partners. your products on this side are going to be AY and XB. So first, write out what the products are, and then use your solubility rules, the ones that we looked at last week. Use the solubility rules to determine if these products are going to be aqueous or solid. So you'll put that behind them, either AQ or solid, and that's based on whether they're soluble or not. Both of our reactants are soluble. Are our products soluble? You're going to have to use their solubility rules to determine that.